Let us now see how the discussion in the previous video, which is video number 11, how that applies to our example 18.6, our cost minimization problem. So just to recap, I said that if I want to find the derivative of the optimal value function with respect to a particular parameter, let's say RT, that can be calculated simply by taking the partial of the Lagrangian with respect to that parameter and then evaluating it at the optimum. So let's see what exactly we mean by this. And we'll talk specifically with respect to example 18.6, where the problem was to minimize R times K plus W times L subject to K to the power half L to the power 1/4 being equal to some output Q bar. And here our Lagrangian was W, sorry, I keep writing WK, RK plus WL plus lambda times Q bar minus K to the power half L to the power 1/4. So we said here that our optimal value function is W R times K star plus W times L star, and this we said was a function of the parameters. So if you look at the expression that you got for C star, that's going to be entirely a function of the parameters. So it's going to be a function of R, W, and the constraint constant Q bar, which then puts us in a position to calculate the partials of the optimal value function C star with respect to R, W, and Q bar. Now, what the envelope theorem is saying is, you have already done the long way. That's also part of the envelope theorem result. In 18.6, you calculated these partials. So if I now try to do things with the shortcut, so the envelope theorem says is, what it says is that if I take the partial of this optimal value function with respect to, let's say, the price of capital R, that is nothing but the partial of the Lagrangian with respect to R evaluated at the optimum. This expression, whatever partial you get, that has to be evaluated at the optimum. Now, this is something very simple. Just take the Lagrangian function. This is your Lagrangian. Take the partial with respect to R. What are you going to get? This is the only term that has R, and the partial with respect to R is going to be nothing but K, and then evaluate it at the optimum. So once I evaluate K at the optimum, I'm going to get my K star, and this is exactly the result that you got in your calculation of 18.6. But note that there you did it in a very long roundabout way, which was what I was illustrating in the example from Snyder and Nicholson also. That was a long way. This then gives you a very short, quick way of calculating the partial derivative. Similarly, you can see that if I were to take the partial with respect to the price of labor, that's going to be nothing but the partial of the Lagrangian with respect to W, which is going to be L, and that you'll evaluate at the optimum. Again, so simple. And last but not the least, if I take the partial with respect to the constraint constant Q bar, so no two guesses for what you're going to get. That's going to be nothing but lambda, and that's exactly what we had talked about in the lecture on the interpretation of the Lagrangian multiplier, that the Lagrangian multiplier is nothing but the derivative of the optimal value function with respect to the constraint constant, and that's exactly what you're getting here. Partial C star by partial Q bar is nothing but the partial of the Lagrangian with respect to Q bar, which is lambda here, and just again evaluated at the optimum, and that's lambda. So this is your envelope theorem, and you can you should now be able to appreciate how powerful this theorem is, because this is providing you with this shortcut to calculate your derivatives. Now what you can do as homework is take up this, let me take a new sheet. Take up your utility maximization problem, the problem that we had taken up in one of the earlier lectures, where you were maximizing x times y with respect to x and y, such that you had taken the budget constraint as 2x plus y equal to something. So let's keep things very general, such that the price of x times x plus the price of y times y is equal to, let's take m. So here so if I call this my utility as a function of x and y, here your optimal value function would be a function of the parameters px, py, and m. Just calculate it. So do the long calculation the way we did it in the original 18.6 example, and then use the envelope shortcut to see what exactly you'll get for partial u star by partial px. Calculate partial u star by partial py, and calculate partial u star by partial m. And do it both ways, the long way and the short way. So ultimately you have to understand how this shortcut gives you a very easy way of finding the result. Okay, thank you.